Okay, welcome everyone. In the last lecture, we have talked about the spin, but we are kind of running out of time. So let's go back to where we start. So in the previous lecture, we talked about electron spin. So up until now, we have been discussing orbital angular momentum, how an electron moves around a nucleus. Now we need to look at the intrinsic angular momentum of electron itself. So this is intrinsic angular momentum. We are going to start with an analogy. So let's build the mathematical framework for spin by borrowing directly from what we already established for orbital angular momentum. Orbital angular momentum. So let's write down some expression for the total angular momentum square, and its eigenfunction is spherical harmonics, and its eigenvalue is h bar square l plus 1, like this. And about the g-axis angular momentum, they share the same eigenfunction, but their eigenvalue is different. So when so total angular momentum square and g-axis component, and we are going to use this exact same algebra structure for spin. So let's write down the similar expression. So s square for up spin up alpha state, that will give you h bar square ss plus 1 and spin alpha. And similarly for spin beta, here. And let's take a look at g component. That will be 1/2 of h bar alpha, and for beta that should be -1/2 h bar beta. So this tells us that the projection of spin on the g-axis is quantized to either plus or -1/2 h bar. Right here, here, and here. And a common question might arise: what actually are alpha and beta? Do they like dumbbells or spheres like the orbitals? So if you look at the section on spin functions, we note a formal association. You could mathematically think of alpha as a spherical harmonics with half integer indices. So alpha as spherical harmonics with half integer numbers, and beta might be 1/2 and -1/2. However, and this is crucial, so this is a strictly formal association. Unlike orbitals, which depend on angle theta and p, Spin function alpha and beta do not necessarily have to be specified in coordinate space. They are quite abstract label describing the intrinsic state of the particle. So we don't need to know what they look like in space. Actually, no one observed that. We just need to know how the operators act on them. And finally, let's calculate the magnitude of this angular momentum. Magnitude of spin. So according to here, the magnitude of the spin should be h bar square root of ss plus 1. Since the spin quantum number small s, spin quantum number for an electron can only have the value of 1/2, we are struck with a very specific situation. In classical physics, we are often recover classical behavior from quantum equation by letting quantum numbers become very, very large. So this is the correspondence principle. However, because S is fixed to 1/2 and is not allowed to assume large values, the spin angular momentum can never assume classical behavior. So this leads us to the statement like spin is a strictly non-classical concept. Spin is strictly a non-classical concept. You cannot think of it physically as a tiny ball spinning on its axis. That classical analogy breaks down. It is a purely quantum mechanical property. Okay, and let's move on to the next page to discuss the orthonormality. Okay, so even though spin is quite abstract, we treat it mathematically as if it depends on a spin variable. Spin variable, so which we denote as sigma. So when we integrate over this variable, we get two results. The first is normalization. If you integrate a state with itself, like alpha with alpha, or beta with beta, the result is 1. And second relation is orthogonality. If you integrate alpha with beta or beta with alpha, or the result is 0. So this simply means the two states are distinct. They are distinct, alpha and beta for sure, and they do not overlap. So you might remember the bracket notation. The equations above can be written in a much simpler way. The first one is like alpha bra and alpha cat, beta bra beta cat, it's like 1, we can write in much simpler way. And let's formalize the notation. Formalizing the notation. Now let's unify our notation. We want the way we write spin to look exactly like the way we write orbital angular momentum. So for orbitals, we use the cat like bar n, l, and m sub l, right? This is spherical harmonics with angular momentum L and magnetic quantum number m sub L. So for spin, we swap L for S and ml for m sub S. Since S is always fixed at 1/2 for an electron, our two spin state becomes alpha is state. So the first one is for S and second one is for m sub S. Then what about beta in a bracket notation? Plus 1/2 and minus 1/2. So notice that when the operators S square acts on the cat vector S m sub S, it pulls out the eigenvalues h bar square S, S plus 1, exactly as we would expect. And the orthonormality conditions might be S m sub S, S m sub prime, that should be delta ms ms prime. Because S is fixed at 1/2, so we have only possible variations for m sub S. Okay, and let's talk about spin orbitals. So now we arrive at a critical concept for the rest of the course, the spin orbiter. Up until now, our wave function, psi, r, theta, and p, only told us where the electron was, like the electron position. But the complete description of an electron must include both spatial distribution plus its spin state. So we construct this by simply multiplying the spatial part of the spin part, as we can see in the equation below. So capital psi with 4 quantum number and L, m sub L, m sub S, and we need 4 independent variables r, theta, p, and m sub S. Oh, sorry. So spin variable is sigma, right? Yeah, that's my mistake. Actually, this is consisting of 2 parts, like spatial part and psi and L m sub L multiplied by spin part. So maybe you want to use the beta here. So because of this, we now require 4 quantum number. Okay? So let's look at the concrete example at, let's go a little bit down. Here we have the ground state of hydrogen 1s orbital. And we can have the 1s alpha state spin up and 1s beta state. So it is like 1s orbital is occupied by alpha spin and 1s orbital is occupied by beta spin. So the notation is like n l m sub l m sub s, right? So 1s alpha is like 1 0 0 plus 1 half, and 1s beta is 1 0 0 minus 1 half. And let's talk about their energies. Spin independent Hamiltonian. So Hamiltonian H is an operator, is the operator that corresponds to the total energy of the system. In the standard Schrödinger equation for the hydrogen atom, the Hamiltonian consists of two things. As you may know, the kinetic energy part, how fast the electron is moving, and the potential energy part, the electrostatic interaction between the negative electron and the positive nucleus. So the key point here is that neither motion nor the electrostatic attraction, Coulomb's law, depends on which way the electron is spinning. So they don't care about the way the electron is spinning. The nucleus attracts a spin-up electron with the exact same force as a spin-down electron. Because the Hamiltonian only includes the electrical force, it is mathematically blind to the spin state. So this Hamiltonian is blind to a spin state. So it effectively ignores the alpha or beta part of the spin function. So this leads to the degeneracy of the system. Because the Hamiltonian doesn't care about electron spin, the energy calculation returns the exactly same result regardless of the spin quantum number m sub s. So like psi n l m sub l and alpha, this will gives energy E n, because the energy of the hydrogen atom only depends on the quantum number n. And psi n l m sub l beta, it also corresponds to energy En. So in quantum mechanics, when two different distinct states have the exact same energy, we call them degenerate. You might remember. Okay, so that's it for section 7.5, and let's move on to next section. Okay, section 7.6 is about the spin-orbit interaction, and it affects the energy of hydrogen atom. So in the previous page, when we discussed the Hamiltonian doesn't see spin. The energy of the electron doesn't care if it is spin up, alpha spin, or it is spin down, the beta spin. So that means the wave function psi n L, m sub L alpha has the exactly same energy as n L m sub L beta. They have the same energies. So this is the standard Schrödinger picture. But nature is more complex than that. We now move to spin-orbit interaction. So to understand this, we have to think of electron as a magnet in two different ways. So first, the orbital magnetic moment. Magnetic moment m sub L. So we are going to use the large capital L to denote orbital magnetic moment. So by orbiting the nucleus, the electrons act like a current loop, creating a magnetic field, and this is related to orbital angular momentum L. So this value is given as unit charge E divided by 2n mass of the electron and orbital angular momentum L. And the second part is the spin magnetic moment. M sub S is G E divided by 2ME and S. So here M sub L and M sub S, this is not magnetic quantum number. So they are the magnetic moment from orbital motion and spin motion. So as I mentioned, the electron has intrinsic spin, so it acts like a tiny bar magnet spinning on its axis. So that causes this magnetic moment. So notice a key difference in these two equations. You might realize that. So G is here. This is the G factor. For orbital motion, the ratio of magnetic moment to angular momentum is standard. But for spin, this ratio is roughly twice as large. So G is like 2. So we used to call this anomalous, but Paul Dirac later showed that this comes naturally from relativistic quantum mechanics. So we are not going to talk about that, but you can accept the result from relativistic quantum mechanics. And now talk about the interaction between orbital magnetic moment and spin magnetic moment. Interaction term. So now what happens when you have two magnets, the orbit and the spin, in the same atom? They should interact. This leads us to equation, Hamiltonian equation, kinetic energy, potential energy, plus spin-orbit coupling. So this spin-orbit coupling term looks like C and orbital angular momentum inner product with spin angular momentum. So this term represents the energy cost of the electron's spin aligning or opposing its own orbital magnetic field. So fortunately, this this effect is quite small, so we can use perturbation theory to solve it without starting from scratch. Okay? And let's talk about the total angular momentum. Angular momentum J. Here is the mathematical consequence of turning on its interaction. Because orbital angular momentum L and spin angular momentums F are now coupled, so they are no longer independent constants of the motion. So mathematically, L square and S square, they no longer commute with the full Hamiltonian. Because of this spin-orbit coupling term. So we define a new conserved quantity. New conserved quantity J. The total angular momentum, which is the sum of the L plus S. So instead of distinct small l and s, we now describe the system using the angular moment quantum number J and Mj. As you can see in this equation. So J square operated on JMJ. Eigenvalue is like this. And for JG operated on JMJ, that would be H bar MJ JMJ. Then how do we calculate the possible values for J? So addition of two momenta L and S. We use the rule of vector addition. So for a single electron, for a single electron, S is always 1/2. So for a given orbital level L, the total angular momentum J can actually take two values, L plus 1/2 and L minus 1/2. So let's walk through the example. So what about L equal 1? So this is like atomic p orbital. So the degeneracy of this system is 2 multiplied by 12 plus 1. So that means you have 6 total states. The 2 is from spin angular momentum, and this degeneracy is from orbital angular momentum. So there are 6 states. So basically they are just like there are 3 p orbitals, and if you put a single electron and 6 possibilities, up spin here, down spin here, up, down, so we have 6 possibility, right? So let's talk about this in terms of total angular momentum J. So one possibility is for J is L plus 1/2. So the 3 over 2. And this state has four possible orientations. So Mj should be right. And the other possibility is J 1/2. And this state has two possible orientations. Mj is plus half and minus half. So if you add up 4 states and 2 states here, the total number of the states would remain the same, right? So 6 states here, and we also 6 states here. Okay, then let's move on to the next section. Okay, section 7.7 is the electronic energy levels of hydrogen atom are described by Thom symbol. So here we are going to talk about Thom symbol. So especially let's focus on atomic Thom symbol. We understand how angular momenta couple together, like spin angular momenta and orbital angular momenta, and we need a standardized language to label these states. So we call these labels atomic Thom symbol. So for a single electron like hydrogen, we often use the notation L with total angular momentum J and spin quantum number here. So because for hydrogen we have a single unpaired electron, so the spin quantum number, total spin angular momentum should be 2. However, as we move to multi-electron atoms, we are going to use the capital letter. So capital L with capital J here. And spin angular momentum will be placed here. So let's break down what this symbol tells us. So the letter L. This tells us the total angular momentum. Total angular momentum. So just like before, L should be equal to 0 is an S state, and L equal to 1 is a P state. So L value and the 0, 1, 2, etc. So for here, S state, P state, D state. So this is very similar for the atomic orbiter symbol. And the superscript 2s plus 1. This is called multiplicity. So it tells about the spin degeneracy. So for a single electron where spin is equal to 1/2, the multiplicity for this case, small s is equal to 1/2. So capital S, which is defined as 2 multiplied by small s plus 1, should be 2. That's why we have 2 here. And according to the 2s plus 1 value, if this is equal to 1, we called singlet 2. doublet, 3 triplet, etc. And the last one is subscript j. As you know, this is the total angular momentum. So total orbiter here. So L is for orbiter and S for spin, and J is their sum, total angular momentum. So this is calculated as L plus S, and we have to care that this is vector summation. So now we are ready to talk about selection rule. So now suppose we have an electron in an excited state and it wants to fall down to a lower energy level and emit a photon. So can it jump to any level it wants? The answer is absolutely no. It must follow specific selection rule. So the first rule is the change of the total orbital angular momentum should be plus minus 1. So orbital angular momentum must change by exactly 1 unit. So why? Because the photon itself carries an intrinsic spin of unit 1. So photon has its intrinsic spin h bar. So to conserve angular momentum, the atom must give up or gain exactly that amount. So this means an electron cannot jump from an s orbiter to another s orbiter. So from s to s, that means the change of the total orbital angular momentum is equal to 0. So this transition couldn't happen. Okay, and the second rule is delta S should remain the same. The spin state does not change during an ordinary electric dipole transition. So if you are start as singlet, then you end up as a singlet. So spin flip is not possible. And rule 3. The total J value change should be 0 or plus minus 1. So, but there is an exception. So transition from J equal to 0 to another J equal to 0 is not possible. This is related to the photon's intrinsic spin. So if you want to emit the photon, then the total angular momentum should be changed, like these cases. And even though we haven't discussed, but there are some cases where the spin flip is allowed due to the spin-orbit coupling. So we can also have some situation like this. So when the change in the J value equal to 0 is like we have delta L plus 1 and delta S equal to minus 1. So rule 3 is the followed by the previous two rules. And let's talk about the Lyman series and fine structure. Lyman series and fine structures. So let's apply this to hydrogen atom to see the real world effect called fine structure. So we are looking at the Lyman series, which involves the transition following down to the ground state n equal to 1. So these transitions correspond to Lyman series. So specifically, look at the transition from n equal 2 to n equal 1. So we discussed that delta L should be changed by 1 unit. So that means the transition from 2s to 1s, this is not allowed. So we are going to focus on the transition from 2s to 2p to 1s. Okay, so this is allowed transition. So without spinor recoupling, we would expect to see exactly one spectral line at 82,000 to 58.19 wave number. But because of spinor recoupling, the 2p level splits into two slightly different energy levels. Due to the spinor recoupling, p j equal 1/2 and another 2p is j equal 3/2. The corresponding term symbol should be p2 1/2, 2p 3/2. Because these two upper states have slightly different energies, they produce two slightly different photon frequencies when they fall to the ground state. So the ground state term symbol should be 2s 1/2. So the first transition, so if we describe this one, so without spinor recoupling, so 1s orbital is here and 2p orbital is here. So there is no splitting in 2p orbital, so we just have the single line corresponding to 2p 1s. But actually, if we have a really good spectroscopic tools, then we can magnify this transition. And actually, they are split into two levels. So the upper one is and the lower one and 1s is just here. So that means we are going to see two slightly different energy levels. So as you may imagine, the changes between these two numbers is only 0.37 wave number. So this is quite small number. Okay. So this is with spinor recoupling. So the real world looks like this, but we don't have enough resolution power, so we observed such one line, but the reality is they consist of two lines. Okay, and let's move on to the Ch7 effect in the next page. Okay, let's move on to section 7.8. So the spectrum of atomic hydrogen in an external magnetic field is accounted for by the Ch7 effect. So from now on, we are going to discuss the effect of the external magnetic field on hydrogen atoms spectrum. So we have already seen that the internal magnetic field of the atom causes fine structure, intrinsic magnetic field, which means the coupling of the spin and the orbital angular momentum. This results in fine structure. So we see that the transition from 2p to 1s is actually doublet rather than singlet. So now we ask, what happens if we place the hydrogen atom inside a strong external magnetic field? So this phenomenon is called Ch7 effect. So we are studying the transition from the 2p orbiter down to the 1s orbiter. H atoms 2p to 1s transition. So based on simpler theory, what we call the normal Ch7 effect, we might expect the spectral line to split into just three components. So L equal to +1, 0, -1. But however, experimentally, when we look at the 2p to 1s transition, we observe 10 lines. So our expectation is just 3 lines, but experiments, there should be 10 lines. So why the discrepancy? So the answer, once again, is spin. Okay, so let's talk about the interaction energy. To understand this mass, we look at the magnetic moment. So we have the orbital moment, m sub L, and the spin moment, m sub S. And the external magnetic field, let's assume that external magnetic field aligned along the g-axis. External magnetic field along the g-axis. So let's call B sub G. So this interacts with the total magnetic moment. So this interaction gives us the potential energy term V, given as follows: 2m. Oh, sorry. So we don't need the absolute we don't need to take the absolute value for the mass because it is already positive value. Lg plus so notice that tricky little g next to the spin operator here. So this is the spin G factor. So this value is approximately 2. Because spin responds twice as strongly to the magnetic field as the orbit does, so L and S don't contribute equally. So this inequality is what creates the complex splitting we see. Okay, and let's keep going. So now we are going to talk about Lande's G factor. Since the magnetic field is usually weak compared to the internal forces holding the atom together, so we can use the perturbation theory. And we are not going to follow every details, but the final result due to the final result of energy shifting due to magnetic field is delta E. Magnetic field is G JL mu B MJ BZ. So here mu B, this is Bohr's magneton value. So this is constant. And MJ, this is the total quantum number. And BG is the strength of the external magnetic field. So the only thing we don't know is G value. So this is Lande G factor. So this factor accounts for how the total angular momentum J projects onto magnetic field direction. So projection, J's projection onto the magnetic field direction. So this formula is given as let me briefly check the GJL. This is given depending on the J value's relation to L. So for J equal to L plus 1/2, so this is the orbital angular momentum coupled with alpha spin. So this is for J equal to L minus 1/2. So this is the orbital angular momentum coupled with the downspin, the beta spin. Okay, and so we don't need to memorize the derivation right now. So, but we must know the values for our specific states. So for 1s state, the term symbol is, so the G value should be 2. And for 2p, there are two different atomic term symbol, 2p 1/2 and 2p 3/2. So according to this, the G value should be 2/3 and 4/3. So because these G values are different for the upper and the lower states, the energy level shift by different amounts, right? So we have two different J values, and according to this equation, the energy change due to the magnetic field is affected by the Landes G factor, right? So now let's strictly focus our attention on the diagram. So it is the figure 7.13. So your 1s orbiter is split by 2 levels. And 2p is split into 6 different energy levels. So p1/2 is split into 2 energy levels, and p3/2 is split into 4 energy levels. So actually the 2p orbital is split into 6 different energy levels. So according to the selection rule, so we can have the transition like this one, this one, and from the higher p states, you can have this one, but not from here, and like this. So we have a 4 transition from lower p state, and we have the 6 transition from higher p states. So please note that there is no transition from here to down there or here to down there. So according to selection rule, the change in J value should be 0 or plus minus 1. But these transitions with the green dot line, they correspond to J equal plus minus 2. So these transitions are not allowed. Okay, so accounting for the spin angular momenta correctly describes the observed 10 distinct lines in the spectrum. And yeah, this is the end of the discussing hydrogen atom, and let's move on to the multi-electron atom in the next page. The last section in this chapter is 7.9, the Schrödinger equation for a helium atom cannot be solved exactly. So let's write down the Schrödinger equation for an helium atom. Equation for a helium atom. So this is the kinetic energy of the nucleus, and so these terms for the kinetic energy of electrons. But for an helium atom we have 2 electrons, so that's why I use the subscript 1 and 2. So this is first electron and the second electron. And we have the potential energy. So potential energy between nucleus and electron. So the nucleus charge should be 2, so 2 here. And this is the distance between the nucleus and the first electron. There should be minus sign here. And similar expression for the second electron. So this is the interaction energy between nucleus and electron. And the last one is the so this is the repulsion energy between electrons. So this is the Schrödinger equation for an hydrogen atom. So to complete the Schrödinger equation, something like this. So we can group them. We can group each term to make this equation solvable. So for the nucleus term, nucleus kinetic energy, we can ignore them. So according to Born-Oppenheimer approximation, we can assume that the nucleus are fixed at the specific points, and we can, because the electrons move much faster compared to the nucleus, so we can ignore the kinetic energy of the nucleus. And we can rearrange the previous equation. And the similar, so this is the equation for the first electron, and you can write down the similar equation for the second electron, right? So all you have to do is just change R1 to R2, and the remaining term is like this. So let's take a look at each term. So the first one, this term, if you take a look at just these two terms, then this is simply describing the interaction between +2 nucleus charges and the single electron revolving around this nucleus. So this is hydrogen-like ions. And the second term also describes exactly the same thing, because in the nature we don't really distinguish the first and second electron, right? This term. And you may notice that the first and second term, we can solve them analytically, right? So the this situation is simply just changing the nuclear charges of the hydrogen atom of +1 to +2. So mathematically, there is no big difference between them. So we can solve these two terms, but the problem is the last one. So this involves the position of two electrons, the R1 and R2. So this term makes it difficult or like impossible to solve this equation analytically. So that's why we have the approximation method, such as the variation method and perturbation theory. Okay, so that's it for the chapter 7. And we now understand why we cannot solve the Schrödinger equation for the helium atom analytically. Okay, that's it for the chapter 7, and thank you for joining me today. Thank you.